Solvents are important in chemistry, and they're important in our daily lives as well. You're familiar with solvents. Solvents being liquids that dissolve other things, often solids, but not always. Blood is mostly water that has dissolved organic compounds and inorganic materials that need to be distributed throughout the body. When you get to the cell level, the cells are aqueous solutions of chemicals that are supposed to react with each other, and it's the fact that they're dissolved in water that lets them react. Apart from biology, dry cleaning is a process that cleans materials that would be damaged if they're cleaned with water. Dry cleaning is nothing more than using an organic solvent to wet that material and dissolve stains, dirt, whatever's in there, and carry it away as a solution. So solvents are common in our daily lives, and it turns out they're common in the organic laboratory as well. We rarely do organic reactions without dissolving the reactants. That may be because the reactants are solids and wouldn't react with each other as a couple of solids sitting there next to each other. It may be because they're viscous fluids and they don't move around enough. It might be because we only have small amounts of material and we need a solvent to give us some volume for the reaction. Whatever the reason, we pretty much always dissolve organic and inorganic compounds that we want to react together in a solvent. Having said all that, what would we conclude would be important qualities for a solvent? I think of two things in particular that are really easy to articulate. The first one is the solvent has to be something that will dissolve everything that's supposed to participate in the reaction. So it has to be good at dissolving things. And the second thing is it has to be inert to the reaction conditions, meaning it doesn't react under the reaction conditions. So it's dissolving things, but it's not participating in the reaction. That's one of the things that distinguishes solvents from catalysts. Catalysts also make reactions happen, but they participate in some way to make them happen. Whereas with solvents, they're just dissolving everything, they're bringing everything together, they're letting molecules move around freely and bang into each other, and those collisions that actually cause reactions. Well, having said that, what would be important for the solvents for SN1 and SN2 reactions? Let's talk a little bit about the solvent properties that we could be looking at. I've put up here representations of three different categories of solvent that we should consider, and let's say a little bit about each one. In the case in the lower right-hand corner, these guys down here, I've just got a bunch of ovals with nothing else to represent molecules. And these molecules are nonpolar. We remember from discussions about polarity and dissolving things and intermolecular interactions that nonpolar molecules don't interact well with ions or really polar molecules. So if we were, for instance, to put a cation, let's say a carbocation, in amongst a bunch of molecules that are nonpolar, those molecules wouldn't show much interest in that carbocation. They wouldn't interact with it much. They wouldn't stabilize it much. They wouldn't destabilize it, but there'd be very little interaction. And we could say the same thing if we were talking about something that has an anion. Let me just say nucleophile minus to make it clear that it could be relevant to us. If we put something with a negative charge in there, those nonpolar molecules are not going to interact with it. They're not going to stabilize it. It's just simply going to be sitting there. And the solubility of these ionic species that I've just talked about is very, very low. So picking a nonpolar solvent for SN1 and SN2 reactions wouldn't make much sense, would it? Because we know in SN1 reactions we're making carbocations, wouldn't be soluble in a nonpolar solvent. We know in SN2 reactions we use nucleophiles, typically negatively charged, wouldn't be dissolved. So we need to conclude that for SN1 and SN2 reactions, nonpolar solvents should be ruled out. We're just going to say these guys are not candidates for solvents of SN1 and SN2 reactions. Now let's take a look at the same kind of thing if we're talking about polar solvents. And I've represented these polar solvents by a bunch of ovals with pluses and minuses. Polar solvents typically will be able to dissolve ions to a significant extent and polar compounds to a significant extent. So they're strong candidates for being used in SN1 and SN2 reactions. Let's think a little bit more about this. What if we put that carbocation in a polar solvent? So here's our carbocation. Those polar molecules will interact with this carbocation, won't they? And we will see stabilization, where these molecules will migrate toward the carbocation as they orient a negative end toward it. This is an important property of polar solvents for stabilizing cations. And so if we pick a polar solvent for an SN1 reaction, we'll stabilize the intermediate. That will speed up the reaction. At the same time, we're going to create some kind of an anion. And other molecules will orient themselves around the anion to stabilize it. So polar molecule as solvent will stabilize the two species we're forming in the rate determining step of an SN1 reaction. This will make it faster. So we can say that polar solvents are good for SN1 reactions. They have little effect on the starting reactants. It's a neutral molecule, but they have a substantial stabilizing effect on the two products that are being formed in the rate determining step. So in terms of an energy diagram, for an SN1 reaction, the energy curve for this first step would have a very high activation energy for a nonpolar solvent. And in a polar solvent, because the ions you're forming are stabilized, the activation energy is far less. So for the SN1 reaction, polar solvents promote the rates by lowering the activation energy because the transition state is more stable due to solvation of both the cation that's being formed and the anion that's being formed by the polarity of the solvent. Let's look at SN2 reactions. In the SN2 reaction, there isn't a large development of positive or negative charge. The nucleophile comes in, the leaving group leaves, there are partial charges that spread out. The effect of the polarity of the solvent on the transition state is much smaller. But that doesn't mean that the SN2 reaction is unaffected by the polarity of the solvent. It is for two reasons. One is, of course, that we have to have a polar solvent to dissolve the reactants. And the second is that the nucleophile is typically charged, and so the nucleophile will be stabilized by the solvent. Let's illustrate that. The two reactants in the SN2 reaction are a neutral carbon compound with a leaving group. Let's write that as alkyl group with a leaving group attached. This is neutral, and there's little interaction with the solvent molecules. And a nucleophile, typically negatively charged. This is charged, and so there will be substantial interaction with the nucleophile. The anion, the nucleophile, will be solvated and therefore dissolved in solution because those polar molecules will orient themselves in a way to stabilize that negative charge to some significant extent. Now there are two groups of polar solvents. Let's write those down. One group is called polar protic, and included in this group would be alcohols like ethanol, methanol, water, and acetic acid is a common one. And these guys are called protic solvents because they all have a proton attached to a heteroatom. In this case, all of them are oxygen, which is usual. A second group of polar solvents are called polar aprotic solvents. A meaning not, so not protic. And they have structures for the common ones like this. It's a molecule called DMSO. Here's another one, molecule called DMF. Here's another one, acetonitrile. Notice that all of these guys are polar. They've got a polarized covalent bond. There'll be a negative N and a positive N, negative N and a positive N. So they qualify for this kind of interaction with a nucleophile. But they don't have the proton attached to oxygen, so their interaction is far less strong than the hydrogen bonding interaction that nucleophiles have with protic solvents. Take a look. When we put a nucleophile with a negative charge, and those nucleophiles have a pair of electrons, The solvent molecules will reorient themselves to stabilize that negative charge, like we've seen already, but with hydrogen bonding. So in addition to the orientations like this, there's true hydrogen bonding. What this does, in effect, is stabilize the nucleophile very well because the hydrogen bonding is very strong. And now we have a much less reactive nucleophile. So polar solvents promote SN2 reactions, but protic polar solvents do just the opposite. They stabilize the nucleophile so well that it's much less reactive. Here's the energy diagram to show that. For the SN2 reaction, we have a standard energy diagram for the SN2 reaction in a polar protic solvent, where we have the alkyl group with the leaving group attached, plus the nucleophile. And in solvents, where hydrogen bonding is not possible, the reactants are less stabilized, so we have a reaction that makes the same products, but we're starting at a different energy level because the nucleophile is so much more reactive. Large activation energy, polar protic solvents. Much smaller activation energy, polar aprotic solvents. So the SN2 reaction is promoted by polar aprotic solvents. The SN1 reaction is promoted by polar protic solvents. The protic solvents are especially good at stabilizing the anion products of the ionization step, which is the rate determining step. So overall, bottom line, polar solvents promote SN1 and SN2 reactions. Polar protic solvents especially promote SN1, and polar aprotic solvents especially promote SN2 reactions.